Okay, so how do we do electron domain geometry and molecular geometry? You're going to draw the Lewis structure of either the molecule or polyatomic ion. So that was from the previous chapter. And then you count the number of electron domains on the central atom. So that you determine electron domain geometry by the Vesper model. And then you determine the molecular geometry by considering the positions of the atoms only. So here, SO3 on the left, how many electron domain geometries around sulfur? 3. Single bonds, double bonds, lone electron groups all count the same. So there's only 3 domains around the sulfur, so its electron domain geometry would be 3. You can look at the table in your book, or if you've done this long enough like I have, trigonal planar. How many of those electron domains are attached to atoms? All of them. So then the molecular geometry is the same, trigonal planar. So we go to the right where we do the ICL4 minus. How many electron domains are on the iodine? 6. Right? We got 4 bonds, 2 electron pairs. So its electron domain geometry is, I know it's been a while, for 6, it's octahedral. 2 of them, though, don't have atoms attached to them. Okay, 2 lone electron pairs. So 2 lone electron pairs, only 4 atoms attached. Octahedral becomes molecularly square planar. And so there is the SO3, where the electron domain and the molecular geometry are the same. And there is the ICL4 minus. The electron domain is octahedral. But if we take the top and bottom atom off and replace them with electron pairs, then we become square planar. So really what you need to do is look, there's a table in your book that tells you if you have, for example, octahedral, 6 electron domains, if they all have atoms attached, no lone pairs, it's octahedral. If they have 1 lone pair, it then becomes square pyramidal. If they have 2 lone pairs, it becomes square planar. So you just have to basically count. Now, as you saw in the Vesper video, the lone electron pairs in ammonia, you have a lone electron pair above the nitrogen, it pushes a little harder on the hydrogens. Even though the electron domain is tetrahedral, it should be 109.5 degrees, but because that lone pair of electrons is closer, pushes the hydrogens closer together, it's actually 107. Formaldehyde, 3 things, it should be trigonal planar 120. But carbon-oxygen double bond, instead of having 2 electrons in between, has 4 electrons because it's a double bond. So it pushes a little harder on the hydrogens. We have 116 instead of 120, and 122 instead of 116. SF4, and they don't show the electron pair that's missing. You can see from top to bottom, it should be 180. It's actually 173.1 because you have missing electron pair there. It's actually pushing the top and the bottom towards each other. And here in BR5, instead of being 90 degrees, because we're missing an electron pair, here it's pushing harder. It's actually 84.8. So if you have lone electron pairs, it kind of deviate from the ideal. So how do you do geometry of molecules with more than one central atom? Well, here let's look at the carbon atom first. How many electron domains are on the carbon atom? 4. Are they all attached to atoms? Yes. 4 is what shape? tetrahedral. Okay? So we know the geometry around the carbon is tetrahedral. Now we look at the oxygen. How many things are around the oxygen? 4, but so it's tetrahedral electron domain, but we only have it attached to 2 atoms, so the molecular geometry around the oxygen is bent. So if you look at the model here, you can see that this is tetrahedral. Over here, it's bent. So that's why we look at long chains of molecules, especially organic. It's not, it looks like a line, it's not. It's all over the place. So if you look at DNA, everybody knows DNA is a double helix. A lot of it has to do with the molecular geometry. It kind of twists it. So it goes up, and then there's other bonds, hydrogen bonds, that hold the twist in position. So if I look at, this is acetic acid, the first carbon on the left, what would its molecular geometry be? How many things around it? 4, so 4 is tetrahedral. What would the bond angles be roughly? 109.5. If we look at the next carbon, what would its molecular geometry be? 3, trigonal planar. Normally the bond angles would be 120. But we have a carbon-oxygen double bond, so that's going to push the other 2 closer together. So between the carbon-oxygen double bond, it's going to be greater than 120, and between the other 2, it's going to be less than 20. So the last one, the oxygen, molecular geometry is bent. We would expect it to be 109.5 because its electron geometry is tetrahedral. There's 4 things around it. But because we have 2 lone pairs, it's going to be less than 109.5, closer to 105 if you remember the video. And that's what we get. And if you look on the right there, you see the model. So you can see how, even though it kind of looks like it's drawn in a line, it's not really linear. And I love doing models in organic chemistry because you can make things that look like poodles and everything else. So, who cares? So they have different shapes. Who cares? Well, the shape affects polarity. Polarity affects physical properties like solubility. So here we have, let's for example say this is carbon dioxide. Say this is carbon dioxide. Let me get a pen that writes. That's the Vesper. Now, which is more electronegative, carbon or oxygen? Periodic table, which one is further to the right? Carbon or oxygen? Oxygen. So oxygen is more electronegative. So where they share these electrons, the oxygen wants them more. So it's going to be polar. So if I draw the dipole moment arrow, the electrons are going to be shifted this way for this bond. So this bond is polar. So I look at this bond, it's also polar, but which way are the electrons going to be pulled? The opposite way. So even though the bonds are polar, the net overall effect, since I have them opposite each other pulling with the same amount, is 0. So the molecule is nonpolar. Okay. If I look at water, remember we said water was bent. Oxygen is more electronegative. But you see they're not opposite each other. They're on an angle. So now we're dealing kind of vector analysis, if you remember physics. and physics, so they're not pulling. It's like, I'm the oxygen, these are the hydrogen. I'm pulling, I'm dragging them with me. So there's going to be a net overall movement, dipole moment. So water is polar. It has to do with the shape. So if we were just to look at the formulas, oh, CO2, I got an O on each side of the C, H2O, I got an H on the side of the O, they're both nonpolar. No. One's nonpolar because it's linear, the other one's polar because it's bent. Here is trigonal planar, and you see we have atoms on all three sides, the same atom. They all pull the same force, so they all cancel each other out. So even though the bonds are polar, the molecule is nonpolar. And here we have, there's water. So you can see how the vectors go. And top one here is carbon tetrachloride, so it's tetrahedral. Chloride is more electronegative than carbon. So they're pulling, and they're each, so it's symmetrical, so they're each pulling so that the vectors cancel out. So carbon tetrachloride is nonpolar. If we remove one of the carbons and replace it with a hydrogen, CHCl3, you can see the vectors don't cancel each other. So CHCl3 is polar. If I take another chlorine off and put another hydrogen on there, it's still going to be polar. 3 hydrogens and 1 chlorine is still polar. 4 hydrogens in a carbon goes back to nonpolar because it's symmetrical again. Here we have what are called structural isomers. You can see one at the top has, let's say, the white balls on opposite sides of the double bond, and the bottom they're on the same side. So those are actually 2 different compounds. But the one on the top, everything cancels out, so it's nonpolar. The one on the bottom doesn't cancel out, so it's polar. A lot of times in organic chemistry, you do a synthesis and say I was making this, and this is 1,2-dichloroethane, where the green balls are the chlorines. I get a mixture of these two. One's polar, one's nonpolar. I only want one of them. How do I separate them? Huh? I already told you, one's polar, one's nonpolar. A what? How? So if I add water, what's going to happen? The polar molecule dissolves. The polar one dissolves because the rule of solubility in general is like dissolves like. So then I'm left with the nonpolar one. I just filter it. If I wanted the polar one, I would add a nonpolar solvent and dissolve the nonpolar isomer and filter it and have the polar one. So once again, shape determines polarity, polarity determines solubility, and if you know different polarities, you can separate them. Okay. The valence bond theory. Atoms share electrons with an atomic orbital on one atom overlaps with an atomic orbital on the other. Each of the overlapping orbitals contain one unpaired electron. The 2 electrons shared by the bonded atoms must have opposite spins. That goes back to the Pauli exclusion principle. An orbital has a maximum of 2 electrons. They can't have the same 4 quantum numbers. So the last one, the m sub s, has to either be plus 1/2 or minus 1/2. So if one's plus 1/2, the other one has to be minus 1/2. You can't have 2 at the same address. It's a paradox. The nuclei of both atoms attract the electrons of the other atom. That's what holds the bond in place. So This is the valence electron, and here's the nuclei of 1. Here's the valence. So here's the +1, here's the -1. What holds it in place is this also has an attraction here, and this has an attraction here. So they pull each other together. And because of that, they pull, there's directionality in the bond. So if we're talking about ionic bonds, where I have a full plus and a full minus, they attract each other, but it doesn't really matter which way they come together. Here, it matters. It has to come with, just like magnets, it has to come with a certain directionality. Because once I actually create a bridge between the two. So here we see hydrogen atoms coming together, overlapping to form a hydrogen molecule. So hydrogen 1s, the s orbital is spherical, so that's why they make it a sphere. So there you have an s overlapping with an s. The p orbitals, remember, are dumbbell shaped, so you have a p overlapping with a p. You can have an s overlap with a p. So here's fluorine. Here's the orbital diagram for fluorine. So it ends in 2p5. So there's one unpaired electron in the p. So remember, fluorine has how many valence electrons? Add them up. 7. Thank you. So it needs one more. So fluorine comes and forms a diatomic molecule with itself. So this unpaired electron gets together with the unpaired electron from the other fluorine, and the p orbitals overlap, which is what you see on the right. And that forms the covalent bond for fluorine. Hydrogen fluoride. So here you have the s orbital for the hydrogen overlapping with the p orbital from the fluorine. All sounds well and good. And if you look at the potential energy, as the atoms approach each other, the attractive force increases because the nuclei are getting closer to the other electrons. So the potential energy goes down, and when they're 74 picometers apart, that's the lowest potential energy. So that maximizes the attraction of the nuclei for the opposite electron. If you continue squeezing them, now the nuclei are getting closer together. Nuclei are what charge? Positive, so two positives are coming together. It wants to repel. So you can see after you get, there's this happy medium here, or the ultimate 74 picometers. After that, if you start getting closer together, now you're getting repulsion by the nuclei. So the potential energy is going back up. So there's that sweet spot right here, 74 picometers. You maximize the attractive forces and minimize the repulsion forces. And here's where you see the directionality of bonding. So sulfur has 2 unpaired electrons, hydrogen has 1, hydrogen sulfide. You can see how it overlaps, the S with P, and it turns out to be 92 degrees. Yeah. Anybody know where hydrogen sulfide, find it? Probably all experienced hydrogen sulfide. No? Like you ever smell rotten eggs? That's the gas, hydrogen sulfide. Prevalent in oil fires, oil well fires. Highly toxic. Now, when you smell it, rotten eggs, it's a very low concentration. High concentrations, you can't smell it. It just overcomes your nose. You go nose blind. Commercials, nose blind to it. So in the early days of fighting oil well fires, people would be walking and smelling sulfur. Take couple more steps, they wouldn't smell it. They go, oh, it's gone. No, it got more concentrated. They take a couple more steps and fall over dead. The important features of the valence bond theory are when you have singly occupied atomic orbitals, they overlap. And the two electrons that share that overlap orbital have to be opposite sign. And the formation of the bond results in a lower potential energy for the system. So that's really it for the valence bond theory. Hydrogen selenide is also foul-smelling. And there we see selenide has 2 unpaired electrons. So the hydrogen are going to overlap with them. Yep, that's basically what it says. This theory is all well and good, except if I look at CH4, if I look at carbon, it's 1s2, I'm going to do 2s2, 2p2. How many unpaired electrons? 2. How many bonds does carbon form? How? That's where the valence bond theory. How can you form 4 bonds when you only have 2 unpaired electrons? Obviously, we got to modify that theory. So we're going to hybridize. So here you have beryllium. So if you remember the Vesper video, some of the earlier slides, we know beryllium, or BeH2, remember it's an exception to the octet rule. It forms 2 bonds. But if you look at the beryllium by itself, it's got how many electrons? 4. So you have the 1s2, the 2s2. There aren't any unpaired electrons. How can you form a bond? Well, what's above 2s? What comes after 2s? 2p. 2p has 3 orbitals. Now, in the case of beryllium, they're unoccupied. There's nothing in them. There's empty orbitals. So what we do, and they don't really show this here, is we promote one of these electrons to here. That's what that little asterisk means. We've promoted an electron. We've taken it from the 2s orbital, excited it, moved it up into the 2p. So now we have 2 unpaired electrons. We can make 2 bonds. But wait a minute. One of them would come from an S shell, subshell. One of them would come from a P. So we're looking at a spherical one and a dumbbell one. So if I were to look at BeH2, I would expect to see 2 sphericals overlap on this side and a spherical and a dumbbell on the other side. But we don't see that. They're equal. So we do what's called a hybrid. So we combine these 2, and we call it SP hybrid. And we still have the two of the 2 P's left over. They're blank. So now we have the SP hybrid. So here we took the S and the P, and we combine them, and we get this little thing that looks like an SP hybrid. So now they're both equal. So they combine with the unpaired electron and hydrogen on both sides. Everything's equal. So here they do beryllium dichloride. So you can see the green is the hybrid orbital, so you can see beryllium, it combines with the p orbital in the chlorine. All well and good. So sp. Boron, we know boron from the Vespertillion likes to form boron trifluoride. Everyone was perfectly happy. 3 bonds. So boron, to form 3 bonds, according to the valence bond theory, should have 3 unpaired electrons. If we look, I only see 1 unpaired electron. It's 2p1. So I can take that from the one of the electrons out of the 2s2, promote it to the 2p, and remember Hund's rule, you fill up the occupied boxes first. So now I have 1 left in the 2s, 2 in the 2p. I combine all 3 of those, so I have sp2, meaning 1s, 2 p's. Now I have 3 unpaired electrons that are all equal. And I have a 2p empty spot. So sp2 forms trigonal planar. Which is what we see. So basically you get the sp2 hybrid, which looks like that green thing, kind of like a clover leaf. And you can see in boron how that would form with 3 fluorines, overlapping p orbitals of fluorine with the hybrid from the boron. Carbon, which we talked about, we know it forms 4 bonds. We only have 2 unpaired electrons. So again, we promote one of these electrons from the s2 into the vacant 2p. We combine them all, so now we have sp3. Now we have 4 unpaired electrons, all the same, and 4 electron domains form tetrahedral. And there's the tetrahedral sp3. You can see it's tetrahedral, so there it forms CH4. When I took freshman chemistry, this blew my mind. I could never keep track of it. I'm sure some of you are feeling the same way. So to summarize now, we have sp, sp2, sp3. So, how many letters in sp? 2. Okay, we got that part. How many unpaired electrons in an sp? 2. 2 things around the central atom form what geometry? Linear. sp2, how many letters? Total. How many total letters? I have 1 s, 2 p's, that's a total of 3. 2 p's, 1 s, 3. 3 things around a central atom. So I have 3 unpaired electrons. 3 things around a center atom form what? Geometry. Trigonal planar. sp3, how many total letters? 4. Okay, we got that part. Okay. Geometry, 4 things around a central atom. Tetrahedral. Well, we're going to go on because when we get to the third row, we have 3s, 3p, 3d. So if I wanted, remember some of the, we had AS5, remember? Exception to the octet rule. I want 5 unpaired electrons, right? So I can put an unpaired electron in the S. I can put an unpaired electron in each of the P's. There's only 3 P's. I need 1 more electron. Where does he think it comes from? The D. So sp3d has 5 unpaired electrons, and its geometry is trigonal bipyramidal. Pyramidal. And the last one, I need 6 things, so it would be sp3d2. 'Add up all the letters, adds up to 6. 6 things, that's octahedral. So I kind of stumbled on that thing and said, hey, all I have to do is count the letters. And I can tell what the, I don't have to know about all this promotion and all this other theory stuff. So here with phosphorus, like PCl5 rather than ASL5, I have 3s2, and you see I have 3p3. Well, if I promote one of the s2s up to the empty 3d, now I have 5 unpaired electrons. If I hybridize all of them, I got 1s, 3 p's, and 1 d, so I have sp3d. 5 unpaired electrons. And I have 4 empty 3d orbitals. And it kind of looks like that mess. And that's how you get PCl5. Here, remember SF6 was octahedral, so I need 6. Well, what I do here is promote 2 of the electrons, one from the S2 and one from the P, and I promote both of them to the D. So now I got 6 unpaired. And I combine all the ones that have electrons in it. So I have 1 s orbital combined with 3 p's and 2 d's. I have sp3d2. I have 6 unpaired electrons. Now I can make SF6. So you have to remember, and that's kind of what it looks like. All these theories came about because we knew these compounds. We had them. Vesper was good for a while, but Vesper doesn't explain the exceptions to the octet rule. We shouldn't have CH4 according to Vesper. According to valence bond theory, we shouldn't have that either. But we know we have it because it exists. We can't, methane exists. So how do you explain it? So they've come up with this hybridization theory to explain that. So here we see sp is linear, sp2 is trigonal planar, sp3 is tetrahedral, sp3d is trigonal bipyramidal, and sp3d2 is octahedral. It turns out so far that's all we need to know. I don't need to move it upstairs. Okay. So in general, how you do this, you draw the Lewis structure, count the number of electron domains on the central atom. That's the number of hybrid orbitals necessary to account for the molecular geometry. It's also the number of atomic orbitals that have to undergo hybridization. So you draw the ground state orbital diagram for the central atom, maximize the number of unpaired valence electrons by promotion, combine the necessary number of atomic orbitals to generate the number of hybrid orbitals. It sounds more complicated than it is. and put one electron in each orbital before pairing. So here, if we look at NH3, it's trigonal pyramidal. We have 3 equivalent NH bonds. So what's the electron geometry around the nitrogen? How many things are on nitrogen? 4, so it's going to be tetrahedral. So my hybrid has to be which one of these? SP3, because it's got to come up before. So I'm going to combine the S and the P. Am I promoting anything? Well, if I do SP3, so I got now 4 SP3 orbitals, so they're all the same. 3 of them have unpaired electrons, 1 of them is paired, right? So if I look at that, the 3 that are unpaired take a hydrogen. So the one that has the 2 electrons in it, that's that lone pair on the top of the nitrogen. So remember, the nitrogen was up there. These are the unpaired sp3 orbitals, and this is the one sp3 that has the 2 electrons in it. So we got 4 orbitals, tetrahedral, except one of them has a lone pairing. What about multiple bonds? Why are we dealing with this? Okay. So if I look at ethane here, ethene rather. Okay, there's carbon's ground state. What is the configuration around the carbon? How many domains are around the carbon? 3. So I know its hybridization's got to be what? Yeah, it's got to, well, I want the letters. sp2. Okay. So I'm going to start, I'm going to do the promotion, right? So I have, if I hybridize them all, I come up with sp3, right? But I don't need sp3, I need sp2. So I hybridize the s and 2 of the p's. So I have sp2, right? So these are my hybrid. And I'm left over with a p electron. Okay. The sp2, we say, forms what molecular geometry? Trigonal planar. So here's my carbon. Here's my trigonal planar. Okay. So I have another carbon. It's going to be the mirror image of this. It's on the other side. Here's my other carbon. So there's its sp2 hybrid orbitals. So this one goes with an H. This one goes with an H. This one goes with a hydrogen, and this one goes with a hydrogen. So that takes care of all the sp2. But what was left over? And 1, 2p. So each one of them has a p electron. P is what shape again? Orbital? No, what shape orbital? S is spherical, P was dumbbell shape. I'm going to try doing this. I'll try this at home. Okay, so I'm going to do a really exaggerated P orbital, perpendicular to this. So there's my dumbbell. Actually, I'm going to... There's my dumbbell. So this one has the same thing. So these p orbitals overlap. So that's what creates the double bond. So now I have 2 electrons here, and I have 2 electrons in the p orbitals. Double bond is 4 electrons. We call this part of the double bond sigma bond. And this part, where the p orbitals overlap, we call that a pi bond. And that's kind of what it looks like. See, we formate the sigma bonds. So that is sigma bond. Sigma bonds are the hydrogens. Then the p orbitals are normally drew like this, simplified, but that's the actual shape where they overlap. So that forms the pi bond. So a double bond consists of a sigma bond and a pi bond. Okay, we okay on that? Kind of think about it for a while. This is the more conceptual stuff. So here we have an example. This is thalidomide. Anybody know what thalidomide is? Was? Is? Thalidomide is responsible actually for the FDA getting as much power as it has. Back in the 50s, the FDA really didn't have much power, not like it does today. And over in Europe, they came out with this drug called thalidomide. It was a tranquilizer used predominantly for pregnant women because apparently pregnant women have moments of anxiousness. Surprise, surprise. So they gave it to them, all right, to help relax them. They helped relax them. And they wanted to get it marketed in the U.S. And there was a woman at the U.S. who, for some reason, said, no, something doesn't look right. We're going to hold off on this. Well, it turned out that thalidomide produces very serious birth defects called teratogen. So they had hundreds, if not thousands, of babies born over there with very serious birth defects. Things like flippers for arms and legs, rather than arms and legs, because it stopped the development. And just by a stroke of luck, she didn't approve it for use in the U.S. Nobody in the U.S. got it. And it turns out thalidomide really is a mixture of what they call stereoisomers. This is just an aside. Stereoisomers are like your hands, they're mirror images, but you can't superimpose them. You do this, the thumbs are on the opposite side, so they're different. Well, it turns out one form has tranquilizing effects. The other form causes the birth defects. Nobody knew about it at the time. Now we know about it, and we can separate the two. It turns out they're actually starting to market the one with the tranquilizing effects again because it's useful in treating leprosy. And the whole thing comes down to that one carbon atom right there. There's a difference. It's called the chiral center. But that causes all the problems. Determine the number of carbon-carbon sigma bonds and the total number of pi bonds. Well, every single bond is a sigma bond, and every double bond is a sigma and a pi bond. So let's count the single bonds. And if we go around the 6-membered ring, there's 3. Then the carbon, to where the carbon's double bonded to the oxygen, is 4. The one below it is 5. Start where on this right ring, where the nitrogen is connected to carbon to the top, and it's where we were 3, 4, 5, 6. The carbon over is 7. Carbon down to the carbon double bond oxygen is 8. And then over here, down to this carbon double bond oxygen is 9. So we have 9 carbon-carbon single bonds. So now we're going to count the double bonds. So we have 3 on the ring, 1, 2, 3. The carbon-oxygen double bond is 4, carbon-oxygen double bond is 5, and the 2 on here are 6 and 7. So there's 7 double bonds. I'm just going to put 7 double. So for this 9, we had 9 sigma for the 9 single bonds, 7 double bonds, and what are we counting? We're counting the total number of pi bonds. Well, every double bond has a pi bond. Okay? So there's 9 pi bonds. Well, carbon-carbon sigma bonds and a total, because if we go back, there's 3 carbon-carbon double bonds there. Out of the 7, 3 are carbon-carbon double bonds, 4 are carbon-oxygen double bonds. So every double bond also contains a pi bond plus a sigma. So if there's 3 carbon-carbon double bonds, we have 3 more carbon-carbon sigma for a total of 12 carbon-carbon sigma bonds. But there's a total of 7 pi bonds. So we looked at, in this case, this is 1,2-dichloroethane. See, there's chlorine on the first carbon, chlorine on the second. We just have a sigma bond in the middle. So, free rotation, you can take those 2 carbons and spin them. So we only have 1 compound. No matter how I draw it, those 3 different, it just happens to look how I spin it and stop it. So they're all the same because they're continuously spinning. So it's just 1 compound. If I stick a double bond in there, now I have the pi overlap, I can't rotate those 2 carbon bonds. You see the one on the left has the hydrogens both on the top. The one on the right has a hydrogen on the top and a hydrogen on the bottom. Those are 2 different compounds. Structural isomers. The one on the left, where they're on the same side, is called cis, CIS. The one where they're opposite are called trans. Different compounds, different physical properties, different chemical properties. Now, again, we're starting from carbon. This time, we do our promotion. And instead of hybridizing 2 of the P's, we're going to hybridize 1 of the P's. So we have sp. So sp, the carbon has how many regions around it? 2. sp, there's 2 letters. So here's 1 sigma bond here. Here's 1 sigma bond here. Here's another carbon with 1 sigma bond. 1 sigma bond. We'll make these with hydrogen. What's left over? 2 of the P electrons. But we already said for a double bond, there's the P orbital, another P orbital. So this is a pi bond, that makes the double bond. But we can also do another one perpendicular to that one, and I can't draw it, so I'm going to show it to you. So it overlaps the other way, 90 degrees. So now I have a sigma, 2 pi bonds at 90-degree angles to each other. That's a triple bond. Because this pi bond here has 2 electrons, and this pi bond has 2 electrons. So a triple bond is a sigma bond, 2 pi bonds. A double bond is a sigma bond, 1 pi bond. So let's explain formaldehyde. First of all, what's the electron domain around the carbon? How many things are on the carbon? 3. So what hybridization must I need? sp2. Great, we all got that. Okay. So we see a carbon-oxygen double bond. So what consists of a double bond? We got to have a sigma and a pi. Okay. The oxygen also has what on it? 2 lone pairs. So here's carbon in its promoted state. But we only need 2 of the p's, because you said it was sp2. So we have 3 sp2 orbitals, and we have p electrons left over. Which is good, because we need that for the double bond. If you look at the oxygen, we have 2s, and there's p's. We hybridize the sp2 there, so we have sp2 where we have 2 of the orbitals are full, and 1 is empty, and 1 has only got 1 electron, and we have a p left over. So, let's look at this. So let's start with the carbon. It's sp2, so its geometry is going to be trigonal planar. So let's draw the sigma bonds. Here's 1. Here's 2, and we know those are attached to H's. Here's 3. And we know this is attached to a oxygen. Does oxygen have an unpaired electron and an sp orbital? What's the geometry around the oxygen? sp2. Okay. So we know it has 1 unpaired electron in the sp. So there's its sigma bond. And it has 2 more sigma bonds, right? It has to be sp2, trigonal planar. I don't know if you can see that. But what's in the other sp2s? How many electrons? No, we already took the 1. 2. So here's 2 here, 2 here. What about the p's in both of them? So here's the p. I'm going to kind of draw it. I don't know the shape of the. There's the p electron for the carbon. Oxygen has 1. So what do we have between the carbon and the oxygen? We have a sigma and my bond, we have what? Double bond. So if I look at it, I have the oxygen, double bonded to the carbon, carbon, single bond to the hydrogen, trigonal planar, 2 electrons here, 2 electrons here, trigonal planar around the oxygen. And that's what it looks like. They don't do it as well as I do, but. So that kind of explains the geometry and where everything goes. Okay. Didn't quite explain everything. So Lewis structures and valence bond theory do not enable us to predict some important properties of molecules. Diatomic oxygen is paramagnetic, so it's attracted by magnetic fields. Diamagnetic substances are weakly repelled by them, and that has to do with the molecule's electron configuration. So, if all the electrons are paired, it's diamagnetic. If they're unpaired, it's paramagnetic. So here you see the picture, they're pouring liquid oxygen, obviously very cold, through a magnetic field. And it's, I don't quite see it there, but it's actually attracted to one of the poles of the magnet. So none of this stuff that we said before explains that. That would be too easy. So now we have to do what's called molecular orbital theory. We've been doing atomic orbitals, now we have to do molecular orbitals. So, according to them, the atomic orbitals combine to form new orbitals that are the property of the entire molecule, rather than the atoms. So we call them molecular orbitals. This is always fun. So they're shaped like, they have specific shapes, specific energies, and a maximum of 2 electrons, just like atomic orbitals. And they have to have opposite spins. And the number of molecular orbitals we get is equal to the number of atomic orbitals we combine. So there, if you're combining 2 hydrogen atoms, and in B, we see on the left there, darker color, we see the molecular orbital. On the right there, in C, you see that the lighter colored orbitals are going the opposite way. Those are called antibonding orbitals. So now we got bonding and antibonding. And if you combine them, you get D, so you see the bonding and antibonding orbitals. So, if I look here, 2 H atoms, both have 1s electrons. We start with sigma 1s. The sigma star, the asterisk one, is the antibonding orbital. The antibonding orbital is higher energy than the bonding orbital. We start filling them up just like we did with electron orbitals. So, the 2 electrons go into the bonding orbital. Yay, we have a bond. Helium, on the other hand, they both have 1s2. So if we were to say, okay, can we make He2? Well, 2 of the electrons go into the bonding orbital, 2 go into the antibonding orbital. Well, it turns out that doesn't exist. You can't do that. And we're getting what's called bond order. Bond order is the number of electrons in the bonding molecular orbital minus the number of electrons in antibonding molecular orbitals divided by 2. So the value of the bond order indicates how stable a molecule is. So if you remember hydrogen, we had 2 in the bonding, none in the antibonding. So it's 2 minus 0 divided by 2 is 1. With helium, we had 2 in the bonding, minus 2 in the antibonding, which was 0. 0 divided by 2 is 0. So it doesn't exist. That's what it just said. Oh. So if you look at lithium, can we make lithium? Well, again, we're looking at the valence electron, so we have the 2s. And what they don't show, so lithium has how many electrons? 3. So if you look at lithium, 1s2, 2s1. So What do we got here? The sigma 1s, then you have the sigma 1s star, and sigma 2s, and then the sigma 2s star. So we have 3 electrons here, and here we have 3 electrons. So you start filling them up. So it's a total of 6. 1, 2, 3, 4, 5, 6. So if you do the bonding, it's 1, 2, 3, 4, minus the antibonding 2, 4 minus 2 is 2, 2 divided by 2 is 1. You can make Li2. But they only show the 2s because obviously these are going to cancel out. So they pick it up with the 2s. So bond order of 1, if we go on to beryllium, we end up with 2 and 2s, 2 and 2s antibonding. You can't make Be2. So there he's showing some molecular orbitals. Okay, and we're going to pick that up next time. Before you